Okay, so now I want to show what happens to the what the Fourier transform does to products. And you might remember from your differential equations class, or let me remind you first of all, before I even get to that, the Fourier transform 1 over the square root of 2 pi. And now we have the integral x going from minus infinity to positive infinity, f of x e to the minus I omega x dx. Now you might remember something called convolution from your differential equations class. And this is a way to take two functions, multiply them in a weird way, as you'll see in just a minute, to get a new function. So the convolution of f and g is equal to the integral y going from minus infinity to positive infinity f of x minus y g of y dy, and by making a change of variable, say u is equal to x minus y or something, this is also equal to the integral y equals minus infinity to positive infinity f of y g of x minus y dy. Okay, now I want to show you what the Fourier transform of the convolution of two functions is. You might be asking, why do we care what the Fourier transform of the convolution of two functions is? Well, you might remember from Laplace transforms, there was a way that the product, you might remember from Laplace transforms that the Laplace transform of the convolution is a product of the Laplace transforms. Something similar will be true in Fourier for Fourier transform. I just want to point out in when you look at the definition in your for Laplace transforms, the convolution here, the integral went from 0 to x rather than minus infinity to positive infinity. That's because in the context of Laplace transforms, you assume that f of x is 0 when x is less than 0. And so if you assume that here, if f is going to be 0 when the argument is less than 0, and if g is 0 when the argument is less than 0, y can only go from 0 to x, otherwise the functions are 0. So it looks like a different definition of convolution, but it really is the same definition. Okay, so what I want to do is I want to compute the Fourier transform of the convolution. I'm just going to start by writing out what this is. So this is going to be the integral. We've got x going from minus infinity to positive infinity, and we're going to have the convolution here. Okay, I think a great way to start is to just write out what the definition is, and that's what we're doing here. And we're going to continue. We're going to say, okay, what is the definition of the convolution? Well, on the inside, the outside integral is still x equals minus infinity to positive infinity. Then we're going to multiply by the convolution, or not multiply, but the convolution is there in the integral. This is the integral y equals minus infinity to positive infinity. And I'm going to use this formula here, f of x minus y, g of y, and then I have e to the minus I omega x, and then dy d omega. This is f of x minus y. Now, since if I take absolute values, sorry, man, what is going on? Sorry, this is one of those times where it's really bad. I really wish I was doing this in person, because if I do things in person, I typically catch the errors as I go, because I can see people's confused faces. I add d omegas, they should be dw's. Okay, if I look at this, if I take absolute values and I do the x integral first, so whenever you take absolute values, you're allowed to interchange the order of integration, because it converges absolutely if it converges in any order of integration. So if you take absolute values and do the x integral, it's going to be the absolute value of x minus y times this. That converges absolutely because we're assuming that f and g converge absolutely, or are absolutely integrable. So if you do the x integral first, if you take absolute values and do the x integral first, the integral of x minus y times e to the minus I omega x. That's just going to be the modulus of that. It's just a modulus of f of x minus y. That converges, or that is integrable absolutely. And then you're just going to be left with the integral of g of y. And that also, since again we're assuming that g is absolutely integrable, that's going to converge. So in other words, if you take absolute values and switch the order of integration, that's finite, which means if you do that, it means essentially that you can switch the order of integration. Okay, so now I'm going to switch the order of integration, and this is 1 over the square root of 2 pi. Okay, I'm going to put the y integral on the outside, so this is y equals minus infinity to positive infinity. I'm going to have g of y, and then I'm going to have the integral x equals minus infinity to positive infinity f of x minus y e to the minus I omega x dx dy. Okay, and I'm gonna work on this integral a little bit, and so I'm not just rewriting a whole bunch of stuff. I'm gonna sort of make changes in place. So what I'm going to do is I'm going to say, look, this integral right here, if I put the 1 over the square root of 2 pi, here, let me just switch this around. So this is the integral y equals minus infinity to positive infinity g of y, and this is 1 over the square root of 2 pi. I'm just putting this inside the integral. This right here looks like the Fourier transform of f, except instead of having just the variable of integration there, I have x minus y. So I'm going to fix this. I'm going to say u is equal to x minus y. Then du is equal to dx. So this will go u equals minus infinity to positive infinity. This is now going to be f of u. And this exponential function, x is equal to u plus y. So this is e to the power of minus I omega u plus y, and dx is equal to du. So we have this. Okay, so that's what we have. Now notice as far as u is concerned, I omega y is a constant. So I can actually factor that out. So I can write this as e to the minus I omega y, and this is just going to be left with e to the minus I omega u. Okay, so now what I have, this guy right here, that's just the Fourier transform of f. And so this is going to be equal to the integral y going from minus infinity to positive infinity, g of y, e to the minus I omega y dy, times f hat of omega. Okay, now this is almost the Fourier transform of g. The only thing that's missing is the divided by the square root of 2 pi. So if I divide by the square root of 2 pi here, I also have to multiply by the square root of 2 pi. And now this integral right here is equal to the square root of 2 pi times the Fourier transform of g, and then times the Fourier transform of f. And so the Fourier transform of the convolution is the square root of 2 pi times the product of the Fourier transforms. As we will see next week when we start looking at solving partial differential equations, what is going to be applied, how we're going to apply this, is we're going to find the Fourier transform of the solution, and we're going to have the product of two Fourier transforms, and we want to find the inverse of that. And that's where the convolution is going to come into play. Okay, that's it for this video, and I think that's going to be the last video that I make this week. Please feel free to look at the exercises and the examples that I have in the notes that I either, sometimes I have them worked out, sometimes they're exercises. Ask me about them or anything else. Okay, look forward to seeing you guys in the discussions.